Well, hello and welcome to the limit of a function. Today we're going to be talking about some limit notation and how that works, and we're going to be connecting it back to some stuff that you've done back in pre-calculus or college algebra. So by the end of the day today, you should be able to identify vertical asymptotes and holes using limits. Now, before we get started on this, we want to have something to reference. So here's a nice little equation that we're going to use extensively here at the beginning of the video. So it might be a good idea to pause this, to graph this, and make sure you label any important features of the graph. Once you've finished that, then you could probably check this on a calculator just to make sure you did a nice job. Now, if you don't pause it, that's okay. I'm going to go ahead and put the answer up here. So here's a little graph that I sketched. You can see we have a horizontal asymptote right here. We have a vertical asymptote here at x equals -2. We also have a hole right here at 2, -1/2. And of course we have our y-intercept at 0, -2, and x-intercept at 4. So these are all the pretty important points that you would want to have on your graph and be able to identify. You would have remembered from college algebra or a previous course that you could factor these, and that if you have similar factors you can cancel, and so that this equation down here is the same as that equation everywhere except this equation is not defined at 2, right? Because if you put a 2 in here, it's not going to work out. So we're going to reference this quite a bit during this video. Here's that same graph on Desmos, and I just did this so that we could come back and reference it and just to verify that we did do it correctly. So the first thing I'll do is I'll put on our vertical asymptote, and we can just slide that right in where it belongs, right there between those two branches. And then here we can bring in our horizontal asymptote, and we'll just slide that in right between the two branches there. Remember, it's going to get really close to it, but in this case it's not going to touch it. It is okay, actually. It's fairly common for a graph to touch an asymptote, but in this case it does not. Like a graph could actually pass over the asymptote infinitely many times, or it could pass through it and then approach it from the other side, but that's not this one. Now, a couple other points of note are that you can see our y-intercept right here at 0, -2, our x-intercept right here at 4, 0, and then right here at 2, you see that this is undefined. And if you look closely, you can see Desmos even puts a little open circle right there, which is probably what you would have done when you were making the graph. That's because the function is not defined there. The function itself will get really close to it, and then it jumps right over that spot right there at 2. You can get infinitely close, but then it just jumps right over it and then keeps on going. Okay, and you guys know that that's at 1/2 because of previous courses. So with this in mind, let's get to it. So we're going to use this limit notation to identify our vertical asymptotes, holes, and today. We're going to not do the horizontal asymptotes so much. We're going to stick with the verticals. Now, as we get started here, the first thing I want to look at is let's figure out on a limit. This one says the limit as x approaches 1 of our function. Now, whenever we want to evaluate a limit, we should always use what's called direct substitution, meaning let's just plug 1 in for x and see what happens. Okay, so if we plug a 1 in up here, I end up getting 1 minus 6 plus 8 over 1 minus 4. So that's going to be 9 minus 6 is 3 over -3 or -1. In other words, when I substitute a 1 in for x, I get a -1 back out. That's my output. And of course we can see if we look on the graph, yeah, that's just right here. That's a point on our graph. The function is defined at 1. The output of the value is -1. And we could see that on Desmos, but this is a little screenshot. We can tell that. Oh shoot, why not? We're right here. So we can see that if we check this here right at 1, that this is in fact -1. It's not, it doesn't say whole or undefined or anything. All right. Now, the fact that this is defined right here, this is going to lead us on to something later on that we're going to called continuity. And it's just that there's no break in the graph right there. The graph just continues right on through when x is 1, it just keeps on going. Okay, you can pass right over it. But we'll look at that another time, so just kind of store that away in your brain too, this idea of continuity. Now, the other thing that we're going to look at is these graphs start to get more interesting whenever the denominators are 0. So let's go back and check this one now. Let's check this as the limit as x approaches 2. Now, from what we graphed before, we know that we're going to have a hole at 2. We already know that from previous classes and spending some time in Desmos. We know there's a hole at 2. Let's look at what the limit looks like as x approaches 2. So we'll just use direct substitution, and we'll put 2 right in for x. So I get 2 squared is 4, minus 12, plus 8, over 2 squared is 4, 4 minus 4 is 0. So what I end up with here is I actually get 0 over 0. So when I have a hole in the graph, I can see that when I do direct substitution, I get 0 over 0. Now this is actually called indeterminate, there we go, indeterminate form. And it just means that we haven't quite figured it out yet. It's indeterminate. We don't know just yet. We still have a little more work to do. But for what we do know, 0 over 0, we can say there's a hole. Okay, so whenever we get to run across this 0 over 0, there's going to be a hole there. Okay, this 0 over 0 is going to approach some finite number. Okay? Now, what we've seen in the past is if we actually take some time to factor this, and we can factor that to be, let's see, x minus 4 and x plus 2. And on the bottom, we're going to get an x plus 2 and x minus 2. Like that. And if we want to take this limit as x approaches 2, we know that we can actually cancel out these common factors. And by doing so, now we can substitute our 2 in using direct substitution. I get negative 2 over negative 4, which, nope. I'm surprised you didn't say anything. Were you just screaming at your screen just now and didn't fix that? Like I factored that wrong. You know, one of the hardest parts about calculus isn't the calculus. It's actually the algebra. This is x minus 2. I know that's probably been bugging you for the last 30 seconds. But I'm glad we got it fixed. There we go. Now, I can cancel out the correct factors and say x minus 2 and x minus 2. And now when I substitute a 2 in for this, I get negative 2 over positive 4. And so negative 2 over positive 4 is negative 1/2. And we can say then that this function, the limit as x approaches 2, is negative 1/2. Now the function itself is not defined there. There is a hole. But you can get infinitely close. You can get as close as you want here on the left side. And you're going to be getting as close to negative 1/2 as you want. And same thing from the right side. You can start to approach this and come at this from the right side and get as close as you want. And even then get a little more closer. Okay, and you can get as close as you want then to negative 1/2. So as we approach 2 from either side, the y value, or the limit, the value of the function will approach negative 1/2. So 0 over 0, there's a hole. All right, let's try another one here. We've got when x approaches negative 2. If I use just direct substitution and put a negative 2 in for this, then I'm going to get negative 2 squared is 4, plus 12, plus 8, over 4 minus 4. So that's 24 over 0. And now whenever you get something like this, 24 over 0, we already know that if you look right here, this is our vertical asymptote. You can't shorten asymptote. I got to write out the whole thing. It's not really a good abbreviation for it. So we've got 24 over 0. Well, if that's our vertical asymptote, what that really means is pretty much any number, right? Any number other than 0, and then divided by 0 is going to imply a vertical asymptote. All right? That's how we can spot a vertical asymptote using limits. Right? If we get some number divided by 0, vertical asymptote. Now, as we look at this, we can see that as we approach this vertical asymptote from the left, the function itself starts to increase. And we could put this in a calculator and check it out. We're not going to. We can check this on the other side too. The function, as you approach that asymptote from the right side, the function is going to decrease. So the main takeaway here, this is what we're looking at. If the limit as x approaches a, any number a of f of x, if you end up getting some finite number, then the function exists at that point. Okay, the function exists there. Now, if your limit as x approaches a is 0 over 0, then that tells us we're going to get a whole. And if you get some number, I guess as x approaches a, if you get some number over 0, that's how you're going to get your vertical asymptote. So that's kind of the main crux of what we're working with here. Now, let's look at a few more examples together. And as always, make sure you pause and just give this a shot. Make sure you can do this. We'll really dive into this in some future lessons, but we want to get the hang of this notation right now. The limit as x approaches 4. I'm going to start with a direct substitution. If I put a 4 in, I get 4 cubed, that's 64, minus 64. Over, let's see, 4 squared, that's 16, minus 16. I get 0 over 0. And so what that tells me is there's a hole. I've got a hole here at this graph. Now, I know how to factor these. This is a difference of cubes. So I'm going to go ahead and factor this apart. This is x minus 4. And then we've got to follow our pattern. So x squared, 4x, and positive 16. Then we do the same sign as we started with, the opposite sign, and then always positive. There. Now we have the factored form of that. This bottom one is a difference of squares. It's x minus 4, x plus 4. And when we want to take this limit, as x approaches 4, the first thing that I'll do is cross these out. Because if I have those factors on top and on bottom, then I'm good. All right. Now, I can actually substitute a 4 in for this, and I get, oh, I almost forgot it. Whew. There we go, that's better. So now I'm going to get a 16 plus 16 plus 16 all over 4 plus 4 is 8. All right, now if I remember right, that's 48 over 8, which is 6. So the limit as this function approaches 4 is 6. Now, the next thing we should do is we should probably graph that and see what that looks like. All right, so here's our function that we have graphed. You can see I've got the function here listed as h, and I evaluated h of 4. And I could come on here and I could try to find 4, and it'll tell me undefined. But I can figure out what that's really close to simply by just putting in like 4.01. Look how close that is to 6, 6.007, right? I could even do 4.001. And look, it's just going to get really close to 6. I can do that from either side. So 3.9999. And look how close that is to 6. So we're coming at this from either side. Now, that tells us then that we did this right, because that is getting really close to 6. The second part of this says evaluate this at -4. Now, when we substitute a -4 in for this, I'm going to get -64 minus 64 over 16 minus 16. That gets me -128 over 0, and this is going to imply that we have a vertical asymptote. There we go. So you have a vertical asymptote at x equals -4. When we go back and check the graph that we were at, you can see that. You can see that right here. Right? In fact, we can even graph this and say, what if we just wanted to graph the line, let's put this up here, x equals -4. If we do that, you can see that's about as good of a fit as we can get. All right? So there's our vertical asymptote there. There we go. Those are our limits. We found the limit here because we got 0 over 0, so we knew there was a hole, and that hole happens at 4, 6. And then over here we've got our limit. We end up with a number on top over 0. That tells me there's a vertical asymptote. Okay. All right, next one. This one looks pretty straightforward. Evaluate the limit as x approaches 2 of this graph. And this is going to be a parabola. So if I put a 2 in, we're just going to use direct substitution to start out with. Then I get 12 plus 12 minus 12 equals 12. That's it, right? We got a finite number. We got a number coming out. So 212 is a point on this graph, and this limit is just 12. That's nice and straightforward. Okay. All right, here's our next function that we're going to be looking at. We've got something, we have x plus 2 over x minus 3 squared. Now, you might remember what this already looks like. But let's go ahead and evaluate it. If we try plugging a 3 in, we end up getting 5 over 0. And so this tells me that I'm going to end up having a vertical asymptote right there. Okay, so I have a vertical asymptote at x equals -3. But we can actually do a little bit more with this when we want to evaluate this limit, because there is this thing where a limit exists if you approach the value from the right. That's what this little plus means. And if you approach the value from the left and you end up, the function approaches the same value, then the limit is said to exist. Even if the function does not, the limit is said to exist there. So if we go back to our problem and we say that, it's not that one, here we go. If we go back to our problem and when we graph this, let's go ahead and clear this out. All right, so we've got our function put on here. And if we look at our line, x equals 3, that's going to be right here. That's where our asymptote's going to be at x equals 3. And we can see that our function, as you approach it from the right, the value is going to get very, very large. And also, as you approach this x equals 3 from the left, the function gets very, very, very large. Now, there's some people that will say that, oh, well, if that's the case, it's not approaching any finite number, and then we would say the limit does not exist. Other people go by the convention of saying, you know what, that's approaching infinity. And so I actually like to say that as well. I would say that as this function, as x approaches 3, then the limit is infinity, and it's positive infinity. It's going up. Again, some people are going to say, well, no, that's not true because it's got to approach a finite number, and there's logical arguments for that. I just think this is a little more, makes a little more sense, and it's more descriptive. Okay? So we do have this vertical asymptote at x equals 3, and that's the main point of our lesson, but the limit does not, the limit does exist. It's at positive infinity for this. Let's look at another one. This one's a little peculiar. And if you try graphing it, it looks extra funny. But if we put a 0 in here, I'm going to end up getting 5 minus the square root of 25 over 0. In other words, 5 minus 5 over 0, 0 over 0. And that tells me that I'm going to have a finite answer. I'm going to have some finite number for an answer. And what I've got to do is I've got to work on this, and this is a little technique that we're going to do in order to try to be able to evaluate this limit. I'm going to take this 5 minus square root t squared plus 25 over t squared, and I'm going to multiply this times the conjugate, 5 plus radical t squared plus 25 all over the same thing, 5 plus t squared minus plus 25. And in doing so, our top is going to, you can FOIL this out, use distributive property on that, or just know that whenever you're multiplying difference of squares, we get the first term squared, and then we get when you have the square of square root t squared plus 25, we end up just getting t squared plus 25. But remember, that's going to be a minus that whole quantity, like that, over t squared times 5 plus root t squared plus 25. Now, it doesn't seem like we've done a whole lot, but just wait. When we distribute this negative t, that's going to be, that will turn this into 25 minus t squared minus 25. All right? So now I can say that the 25 and the minus 25, those cancel out. And then I can also say that, let's see, t squared and t squared cancels out. So those are going to be gone. And all I have left then on top is a negative 1. And all I have left on bottom is 5 plus root t squared plus 25. And now I'm going to evaluate this limit, not as x, but as t approaches 0. So I can use direct substitution now. I get negative 1 over 5 plus 0 squared plus 25. That ends up just being regular 5, and I get negative 1/10. So this limit is negative 1/10. If you graph this, and I'll leave that to you, but if you graph this, you end up getting a hole in the graph right there. It's undefined, but you can see it's getting really, really, really close. The function is getting very close to negative 1/10. All right, let's look at one more problem here, and this is a nice, pretty classic problem. For this function, state the following: the limit as x approaches negative 6. So when I look, right here is x equals negative 6, and the limit would be the y value. Now I can see that this is coming up from the bottom here, and this is coming down from the top there. So the limit of this appears to be 0, because we're approaching 0 from both the left and the right. Okay, what about the limit as x approaches 0 just from the left? All right, well, here's our line. I'm going to make this a little bit darker just to be able to see it a little better. Oops, kind of struggle making lines sometimes. There we go. If I want the limit as b approaches 0 from the left, meaning I'm going to come at it from the left, and we can see that this function is getting larger and larger and larger and larger and larger and larger, right? Because we have this vertical asymptote. So this limit, as we come at this from the left, is equal to a positive infinity. This is going up. What about the limit as we approach this from the right? When we approach 0 from the right, when we start here and we come back this way, the function's going down. Okay, so this is negative infinity. Now what that means is because the left-hand limit doesn't equal the right-hand limit, then the function does not exist. Now, it doesn't actually ask us, but that isn't an observation that you would want to make. The limit as x approaches 0 of g of x does not exist. Okay, it does not exist because the two limits are not the same. What about the limit as x approaches 4? Well, here's 4, right? And we can see this is going down towards negative infinity from the left. This is going down towards negative infinity from the right. And if the left-hand limit and the right-hand limit are both going to the same place, then that means that the limit does exist and it's negative infinity. Lastly, this question, part E, says find the equations of the vertical asymptotes. And all of these vertical asymptotes, they're pretty easy to find, right? We're going to have right here. Whoa, really got, that's just horrible. There we go. Let's try this again. So we're going to go right here. This is 1. That's x equals -5. We're going to go right here. That's appears to be 0. And then right here at 4. So we always want to write these as equations, though, because they're the vertical asymptotes. So this would be x equals -5, x equals 0, x equals +4. All right, well, I hope you got a little more comfortable with this idea of limit notation today, and that you can identify vertical asymptotes and holes using limits. And we'll get lots more practice on when limits exist as well in the future. All right, have a marvelous day.